Aqui? Isso. Pode ser. Boa tarde a todos. Obrigada, Patrícia, por aceitar o convite. A Patrícia é a nossa palestrante de hoje. Ela tem mestrado em astronomia pelo Instituto de Astronomia, Geofísica e Ciências Atmosféricas, o IAG, tanto mestrado quanto doutorado. Ela tem experiência na área de astrofísica, mais especificamente no estudo de núcleo ativo de galáxias. Foi estudante do professor João Stein, atuando diretamente no projeto Diving 3D, e hoje é a nossa convidada. Muito obrigada.
Obrigada. Eu gostaria de agradecer o convite. Para mim é uma honra apresentar meu trabalho aqui. Esse trabalho é meu trabalho do último ano, onde eu trabalhei no observatório. Eu esqueci que eu tinha que falar em inglês, né? A apresentação. Bom, volta. So, thank you very much for the opportunity to present my work here. So, this work was conducted on the last year on the Observatoire de Paris under supervision of Professor Françoise Combes. And the title of the work is Multiple Scale Gas Infall Through Gravity Torques on Milky Way Twins. The title pretty much says everything of this work. It means that we are studying the gas dynamics on galaxies that are similar to our own galaxy, and study how the gas interacts through the gravity torques, how these gravity torques influence the gas to feed the nuclear region of those galaxies. So this image that I chose on this first slide is one of the galaxies of the sample, NGC 1300. And this image is from JWST. And it's pretty nice because we can see the main features and structures of this galaxy. We can see the bar and how the bar is connected to the nuclear region. And we can see also things that are pretty much very present in all the objects of the sample, which are the structures of spirals, nuclear rings, and nuclear bars, and nuclear spirals. So this is a very complex system, and it's a very complex work as well. I ask you guys to bear with me, have patience, because it is a work that I just start doing. I just have a little experience of that, and it's a very complex team as well. So before I start talking about this project, I will give a little bit of context on how this project was born. So the main project I presented last year. You guys can see on YouTube is there still the presentation that I did. So if you guys didn't see yet, is about the study of nuclei of galaxies with the same morphological type. So SABbc and SBbc galaxies of the Diving 3D survey. So this survey has a goal of observing galaxies on the southern hemisphere using optical data cubes. And the sample limit was the magnitude on the B band less than 12 and galaxy latitude greater than 15 degrees. And the sample of the Milky Way morphological twins are 15 galaxies in total. However, in this main project, I also added the non-baric counterparts, SABBCs, in order to compare the influence of the bar in those galaxies. And in total, the sample comprised 23 galaxies. One of the results of this main project is quite surprising, that we found that most of the nuclei of Milky Way morphological twins are active. And we know that the Milky Way is considered not to be active. So this is quite surprising. And they are not that active as well. They are liners, low ionization emitting line regions. Another thing that we found is like the abundance, as I said, the abundance of structures in the nuclear region. So that's what one of the motivation to build this project that I'm presenting today. which is the connections of the bar and the outer parts of the galaxy with these structures in the nuclear region, because it is present in all the sample, in all the galaxies. At least we have not only the nuclear sources, but we have circumnuclear rings or nuclear bars or nuclear spirals, something around the AGN. So why? So the goal of this present work that I'm present here is to quantify the efficiency of the bars in driving the gas towards the nuclear regions and building these structures, and also compare the barrier and non-barrier galaxies and see if the bar is actually the only one responsible to build these structures on the nuclear regions. To do this work, we only need two data. One red image and the data of the gas that I want to see the influence of the torques. So from the red images, we actually get two data from, one from Hubble Space Telescope with the F814W filter, and the other is from Z-band filters, mainly from the Legacy survey. But when the Z-band images were not that good, we used the R-band as well. And for the gas, in this case, we are studying the molecular gas from the ALMA data, using ALMA data cubes, mainly from Fung survey, their public archive, and the transistors are CO221. So, continuing, so this is the data. So one set of data is one red image and the associated molecular gas image. This is one set of data. So each square that you guys are seeing here, this is all the sample of galaxies. I forgot to mention that with the limitations of the sample, we obtained 10 galaxies for this project. Not all of those 10 galaxies are the same of the ones of the Diamond 3D project, because of data variability, mainly. The other fact is that we have to limit this sample with the inclination that has to be lower than 65 degrees, because we have to deproject the galaxy, so very edge-on galaxies will be very imprecise in the work. So each square represents one set of data. So the yellow squares here on these two galaxies, NGC 3000 and 2903, are the ones that we have to combine two data cubes from ALMA to get this very large field of view and legacy image associated with that. The red squares are the legacy image associated with the ALMA image, but with smaller field of view, not that big as the yellow ones. And in many cases, the data cube used for the red square from the ALMA are the same from the green square. However, in the green squares, we use the associated red image from HST that has better spatial resolution. We also have the cyan squares that represent even smaller fields of view from using then HST, but in this case with ALMA data with higher spatial resolution, higher than the other ones. So another thing is that in those images you guys are seeing these lines. They are the position angle of the bar of each galaxy. And you can see that we only have two non-barrier galaxies on the sample, unfortunately, because we don't have enough data. Now, here comes the difficult part. So, for the red images, we aim to get the mass distribution through all the galaxy. Why using red images? Because they are basically coming from the old stellar populations that represents better the stellar mass distribution, and because they are not affected by dust. So with that, from those images, we actually have to cut those images, all of them, the data cubes and the red images, to have the same field of view and the same center, and the center was measured only by the emission peak of both images. and we have to rotate to have the major axis horizontal, just to see the asymmetries better, and to deproject in order to see the tangential forces and the mass distribution of the galaxy. So with that, after all of that, we compute the gravitational potential, and this is the first step. After that, we apply the Fourier transform in order to see the variations of the gravitational potential on the system. And these variations can be, we represent the perturbations of the potential, and each component of the Fourier transform will represent one kind of a symmetry or asymmetry. So m equal 1 represents an asymmetry that could be a loop-sided disk, or when you have one spiral, only one spiral arm. Or when you have two spiral arms, but one of them is more dense or more brighter than the other. So you have asymmetry. This is m equal 1. M equal 2 is a bidimensional symmetry. So when you have bars or spirals, two arms of the spirals and the bar, which is very symmetric in this case. M equal 3 is related to the three-arm structure. So you can have three arms, or you can have two arms, but one of them is branching. And m equal 4 could be four arms, but in this case is actually when you have a square bar, and then you have m equal 4 is more related to the shape of the bar. So m equal 3, m equal 4 are modes that we are not seeing in this galaxy, so they are somewhat rare to see, so we are not discussing more. We will discuss more m equal 1 and m equal 2. The sum of amplitudes of these modes, that is this thing here, the QM represents each amplitude. The sum of amplitudes represent the total perturbation of the potential. When you have like a very strong bar on the galaxy, which m equal 2 will be the main mode, you have that the QT is equal to the strength of the bar. That's what they use to estimate the strength of the bar. Other thing is that those modes have variations of phase with radius. When we have to analyze them to differentiate the structures between spirals and bars. When you have a phase m equal to phase constant, it is a bar. When you have m equal to phase, like it is like varying with radius, you have. Yes. So when you have a variation of the phase, like if you have a spiral. So, okay. So another thing from the gravitational potential is that we can derive the forces, and with that we will obtain the gravity torques per unit mass, which is this equation here. With this, with the gas map obtained from ALMA, we multiply that we can derive the gas density, and we multiply by this equation here of the torques, and we will obtain the influence of the torque on the gas that we are studying. So we will obtain the torque maps that are called torque maps here. So in the torque maps the values are negative, it means the loss of angular momentum, so the gas is falling towards the center. When you have positive values, we have the gain of angular momentum, so the gas is getting out towards the edges of the galaxy. Okay, but it's not that simple. It's more complex than that. We have resonances all over the place. So we have mainly 3 resonances, but you could have more than that, or in some systems only 1, or in some systems the 3 of them. The resonances will make the torques change the signal. So if you have like positive torques, when the gas encounter a resonance, it will become negative. When the gas encounter another resonance, it will become positive again. So the first resonance here is the co-rotation, when you have the orbital angular velocity of a star, for example, that is equal to the perturbation that we are dealing with. For example, if the star is rotating at the same period as the bar, you have a co-rotation resonance. Then we have the inner Lindblad resonance. This one is when the star is rotating faster than the perturbation. In this case, it could be spirals or bars, so the mode m equal 2. That's why we have 2 here in this equation. So we have the star rotating faster than the main perturbation, but the difference between the angular velocities of orbital angular velocities of the two is the epicyclic frequency divided by the resonance mode, in this case, m equal 2. So when you have this specific scenario, you have an inner Lindblad resonance. And the outer Lindblad resonance, when the star is rotating, is lower than the perturbation by the same factor, kappa under 2. By the way, kappa is the epicyclic frequency, is the frequency of oscillation of the star, in this case, on the orbit. So the bar of the galaxy actually can divide the torques in quadrants. So we have, when we have a system with a bar, which is inside this co-rotation radius. By the way, resonances are responsible for the formation of structures in the galaxy. So inside the co-rotation, we have a bar. On the inner and outer Lindblad resonances, we will have the formations of rings. That's why we have outer rings on the galaxies that I'm going to show on the symbol, and we have circumnuclear rings. So the bar will always be the quadrant will always be perpendicular to the major and minor axis of the bar. And that's why we need the position angles of everything right on the bar and also the major axis of the galaxy. So in this case, it's a schematic showing how the torques behave. So if you have a bar galaxy with 2 spiral arms, well, how is the torque in this galaxy? We have the galaxy rotating in this direction, so this is very important, because if it was the opposite way, you have negative, positive, positive, negative. So in this case, the rotation of the galaxy is important to define the signs of the torque. So the positive torques will have the gas to lose angular momentum, and this gas will end up building the spiral arms. So we have a bidimensional symmetry. Okay, so we have spiral arms one side and another. The negative torques will make the gas lose angular momentum and get inside of towards the center. So that's why we don't have gas in these 2 quadrants. So when you have positive gas coming from the arms, it encounters the first resonance, co-rotation resonance. The torques will become negative, okay? And when we get further in, the gas will encounter the inner Lindblad resonance, and the torques will become positive. So what means? When the gas is negative coming from outside of the inner Lindblad resonance, the gas will fall into this orbital region of resonance. Oops. And the gas inside has positive torques. So the gas will be coming from the inside towards the inner Lindblad resonance. So that will accumulate the gas in this special orbit and form the nuclear rings. One thing that I have to say is that bars and nuclear rings are transient features, okay? They can be dissolved with time. the estimation of the major bar is 1 or 2 gigayears, okay, and the rings is more faster than that. And when you have a supermassive black hole in the center, the things become even more complex because the gravitational potential of the supermassive black hole will make the torques change in the center, making the frequency, angular frequency of the things that are inside the inner Lindblad resonance to be faster. So we'll have again negative torques. And then we'll have the formation of nuclear bars and spiral feeding the nucleus. Okay? So that's what we see in those galaxies. Another thing from the gravitational potential is, sorry. So from the image, from the gas map, from the torque from the gas map, we can average over azimuth, and then by normalizing in momentum, angular momentum, and rotation period, we will obtain this very important curve, which is the variation of angular momentum normalized in one rotation versus radius, which represents the efficiency of the gas flow or the loss or gain of angular momentum with the determined ratios. And this is important because we will see, I will show the torque maps. It's very difficult just by looking at the torque maps to see what is the most important thing happening there. So those curves are important to interpret the gas torque maps. Okay, so this is the sample again of the galaxies, and you guys can see something very interesting here. So most of the galaxies, except for this one, it has an outer ring. So we can see the influence of the outer Lindblad resonance in the whole sample, basically. We can also see that the nuclear activity is variable between binaries and regions mainly, but actually there is a huge discussion of every single object about the nuclear activity. Some objects actually have all the classification from A to regions to Seyferts. So we don't know exactly if the nuclear sources of these galaxies are variable or if there are imprecisions of each method towards the time to determine if they are AGNs or not. Okay. However, the sample of the Milky Way morphological twins, as I said, they are mainly AGNs and mainly low ionization emission line regions. So this is the position angles of the major axes that we confirm by seeing the gas velocity maps. This is the bar position angle and declinations. You guys can see that there are objects here that have inclination higher than 65 degrees, but we included because they are within uncertainty acceptable. Another thing is that coincidentally, the total stellar mass of the galaxies of the sample don't vary much between each other, which makes the sample very homogeneous. And keeping in mind that bars are transient features, we can say that this is we can kind of see evolution of the bars and within the life of those type of galaxies, the formation and when they are not there. So I'm gonna show 2 examples because there are 10 galaxies. It is a lot of images in the paper. So I'm not gonna be able to show each one of them. So it's gonna be actually very repetitive. So I'm going to show only 2 examples, one Berry galaxy and one unburied galaxy. And the main features of each one of these 2 groups are the things that we're seeing in the whole sample. So this is one set of data, as I said, HST, ALMA, and this is legacy, and ALMA again is the same data cube, but the field of views are different. I can show here. NGC 4303 is this one. So we can see the legacy field of view is greater than the HSC field of view. or larger. So you can see the bar, the main feature here, and the bar, inside the bar we can see the molecular gas behaving as a spiral. We can also see in the HSC image the circular nuclear ring of this galaxy, okay? And you can see the rotation maps of the molecular gas are very well behaved, and we can see the spiral arms in the larger field of view. And in this image is more clear the bar of this galaxy, which is safer, it is an AGN as well. Okay, so this is the torque maps, and this is the this is the variation of momentum angular in one rotation. So if you guys look just at the torque map, we're not going to understand much of what is happening. But when we look with this curve, we will be able to understand what is the main thing that is happening, main phenomenon that is happening within this galaxy. So we have the 4 quadrants again. They are all related to the bar. So this is the position angle of the bar, okay? So we have positive, negative, and positive. It's always like that. And this is the related to the rotation of the galaxy as well. So we have to take that into account. And we have negative torques in the region of the bar, which is the spiral that is exactly on the bar is located, this spiral here. So we are seeing that these 2 spiral arms are actually driving the gas from the bar to the nuclear region. And we can see that outside the bar, the torque changes because of the co-rotation radius. The torque changes value, it becomes positive, making the spiral arms. It will be positive until the outer Lindblad resonance that we don't have the field of view to see that. But it will become positive until that, and then we invert again the sign, and we have like the ring of the galaxy. So the main torque on this galaxy is negative. Okay, we have loss of angular momentum in general. And here we can see that there is an inversion of torques, the signal. This is because of the inner Lindblad resonance that we revert the torques to be positive. And we actually have the circular nuclear ring, which is where the torque is positive there. That's why it was formed there. And here is the same thing, but with a larger field of view. We can see, again, the positive torque in the region of the circular nuclear ring, negative torques in the bar, and it becomes positive again after the co-rotation radius, and we form the spiral arms. Oops, sorry. So, as I said, we also analyze the amplitudes of the modes of the harmonic from the Fourier transform. So each one of them represents an asymmetry or symmetry. In this case, obviously, we have m equal 2, which is the symmetry. In this case, it represents the bar, okay? But it's not only the bar, because you can see in the phase that is not very constant, like it has a little bit of variation. And this little bit of variation, I understand there is the contamination of this spiral here within the bar. Okay, so m equal 2 in this case is the predominant mode of perturbation of the potential, and the other ones are very close to 0, so they are negligible. We also use we can use many data in order to see the behavior of the torques on the data, and we are experimenting to use on MUSE data cubes using H alpha emission line. So we apply the same method, but instead of using the molecular gas, we use H alpha, and we obtain basically the same map. Okay, the only difference is that the H alpha emission is a little bit more flocculent than the CO, that is more extended. And that will cause these variations on the curve, but in general, you guys can see that it's quite the same. Now, the non-Berry galaxy, this is the best example of that we got from the non-Barry galaxy, which were only 2 of them. We have the HST images, and ALMA is the same data. And here in field of views, different field of views, you guys can see here in this image here, 4689. So we have the legacy data comprising only this field of view, and the HST, which is a little bit smaller in the center. And you can see that different from the other galaxies that I show, there is no clear structure here. We don't see the bar, we don't see rings, we don't even see spiral arms. Okay, it's very difficult to understand in the morphology of this gas. However, the rotation is quite nice. With that, we confirm the position of the major axis that we used. And this is the torque maps and the variation of angular momentum. So, in this case, we can see that there is a very bright presence of positive torques. And there is a presence also of negative torques, but not that much. The main thing here is the positive torques. And in the nuclear region, which is here, we can, I don't think we can see, but the nuclear region is right here, in this point. We can see that there's the predominance of the positive torques, and then we have a resonance that we make the torque change value, or signal, and it become negative. However, as you guys can see in this image with a larger field of view, the positive torques are the predominant thing here. And the negative torques are varying around 0. So, in the case of these galaxies, the predominance are from positive torques and the negative torques are not predominant. So the gas is actually forming spiral arms and not falling towards the nucleus. So this is again, the amplitudes of the modes of the perturbations on the Fourier transform. And we can see exactly the asymmetry. It is the most perturbation here. We can see in the phase, it is related to a spiral because of the variation. And you can see the m equal 1 is one of the predominant perturbations here. And you can see why here, because we have more bright and more relevant regions on the upper part of the map, and in the lower part we can barely see anything related to the torque. So this is the asymmetry. And we also see a little bit of m equal 2, so that could be related to spiral arms, but we're not seeing clearly on the images. So the conclusions are that all the galaxies that have bar on the sample show the strong presence of structures in the nuclear region, and we are seeing that the bars are the main responsibles for the driving of the gas towards the nuclear region to form these structures, to form the circumnuclear rings, etc. Non-Barry galaxies seem to be more flocculent and don't have clear structures. And, well, we started this project thinking about if we could make a direct comparison with the main project, which has scales of 300 parsecs, but we end up having only these scales for kiloparsecs to hundreds of parsecs. And the comparison can exist, but it's not very central in the nuclear regions that are way more complex. We have like changes of torques because of the supermassive black hole and the interference of the supermassive black hole when it's active towards the circumnuclear region. We don't see anything like that here because of the spatial resolution. So we need more spatial resolution in order to see what happens within the inner Lindenblad resonance. And how is the influence of the inflow of gas and the feedback of the AGN? One good example is NG6 613. I invite you guys to read those two articles. Algebert et al. 2019. They are studying the torques of this galaxy in the smaller scale. It's a very detailed work about that. And my work is about the emission and the influence of the AGN within the inner resonance and the connections of the bar with the center. And, well, as you guys can see, there are only 10 objects, so we need a greater sample of non-barrier galaxies because we only have 2 compared with 8. But we need the greater sample to compare if the negative torque will be actually not relevant in those galaxies, if it is confirmed, and to see if there is actually another ways of the gas to fall and form structures on those galaxies that don't have a bar. So this whole work was submitted on Astronomy and Astrophysics journal, and hopefully will be published soon. So thank you very much.
Thank you. We have time for questions.
Hi, thanks for all these results. My main question is about the mass, the estimation of the mass. You said that you took a red filter of Hubble to estimate the mass.
So this is a very complex part of the work because we need the old stellar populations, okay, and with the M under L mass luminosity ratio, we can estimate the mass, but it's not that simple because I don't have exactly. This is not a part of the work that I actually did, so I don't have exactly how it was done. But in the case, it is apply a fast Fourier transform to obtain this potential. So I don't have like the specifics of that, but I invite you to read this paper, Combs and Sander 1981. They explain how they do that.
Okay, and just one question more is, so you see the negative torques, that means that the mass moves toward the center in the bars, and then positive torques that makes the gas to go away. So do you know how to estimate which fraction of the mass of the gas still goes inside, especially for active nucleus?
Well,
just that.
To estimate the mass, I'm not sure. We quantify the loss of angular momentum, but to estimate the mass, I think it's more complex. I'm not sure. We didn't calculate that in this work, but I think it's very complex. I don't know.
Patricia, very interesting results, and you showed on that list that you have samples, you have cases where there is an obvious evidence of observation of bars, and in another sources there is none, and so there is no clear correlation between the presence of bars and the supermassive black hole in some sense, right?
Yes.
On the other hand, I would like to add more complexity to your problem, to this issue, because there is also not only the action of the AGN feedback in this evolution process, but also the wind due to star formation. So you have two components here that may help with this transport of angular momentum that goes in and goes outside into the feedback. And it's interesting because we have performed, and we published this year, a work where we performed 3D simulations of the nuclear regions of these classes of sources that may have the contribution from both the AGN wind outflow and the star formation driven wind, to see what happens in this accretion process and with the feedback in the evolution of the galaxy. And we also identified the formation of rings of enhanced star formation with nothing in the middle, simply because of the action of the AGN as it digs a hole in the middle, and then it goes out and it forms, it allows for the formation of these rings of enhanced star formation. That is, a combination of the two processes, the outflow and the star formation or supernova-driven winds in the nuclear region. And all this happens within 1 kiloparsec region, so it's exactly the same scale. So it's interesting because we did not take into account the presence of bars at all, only the action of these. Of course, there is rotation of the galaxy, so there is gas inflow, but these rings disappear when the AGN wind is dormant. So it's because it goes out for several hundred thousand years, and then it goes down. It vanishes temporarily because of the lack of the absence of mass inflow, because it goes out in the fuel. It goes out in the outflow, so it stops. But then you have the formation of these rings in between in these processes. So do you have an idea of the scale, the time scale of those sources that exhibit the ring structure? That is, in this case, is associated to the inflow and therefore to the bar.
So the time scales are about mega years, I think. I had this conversation with Françoise. She said that the time scales of the bar to be dissolved is 1 to 2 gigayears, and time scales for the ring to dissolve are much more smaller. So she says about mega years. So another thing that you mentioned is that the rings are formed because of the resonance, Lindblad resonance, right?
Because you have this.
You don't need necessarily to have a bar to form these resonances. Okay, only the spirals could have, like, you can have the spirals will be the perturbation on which the gas will rotate faster and
but they should form at
and then
100 parsecs or something like that, right? Or
yes, the co-rotation radius, it could be on these scales. In the Lindblad resonance will be
yes, for these classes,
hundreds of parsecs.
Yeah, for these classes of
yes,
sources.
You can have the outer, which is like 1 kiloparsec. Well, with the edges of the galaxy, right? And the edges of the one will be the edges of the bar, and the other will be the edges of the galaxy. So we have a ring there too.
Right.
So you don't need exactly the bar to form these structures.
Right.
That's what we were expecting to see on the non-Barry galaxies.
Yeah.
But we actually found nothing there.
Right.
But the thing is that it could be the case of the rings are being formed, or it could be the case of the rings are just being dissolved, right? Just finished being dissolved. It's something that is very fast. So it will be like we have to have a good sample of galaxies to see the frequency of the rings on the galaxy that don't have a bar. Another thing is interesting because that's why I cited this work about NG 613. Oops. No, okay. So this work about NG 613, because we found out that the AGN, instead of helping build the ring, it actually the feedback made a break in the ring.
Yeah,
so we have some cases of that. So it's interesting.
Yeah, but I can show you. I can send you the paper so that you take it into the simulation.
Yes, thank you.
More questions?
Thank you, Patricia. It was a really nice talk. I'm wondering if you measure the star formation rate that you have in the the flows, Gauss flows that you have in the inner part, so in the bar.
No, we don't. I don't have an idea.
Okay. And another question: have you, if you have any idea of the sample, the galaxy sample has any evidence of the classical bulges?
Well, in this sample of this work, we don't have, they are all pseudo bulges. However, in the sample of the diving 3D, we have at least one case of classical bulge.
Okay, and how big is the structure? Do you know? Because it's very interesting, based on some simulation that we are doing, analyzing the inner rings in the galaxies like Milky Way. Mm-hmm. So we found that we need to have some pressure supporter structure in order to construct an inner ring. That's why I'm wondering if in this external galaxy it's something like similar.
Well, that galaxy is NGC 6744. There is a paper about that I wrote. You can search if you want. It has a classical bulge, but we don't see nothing, no rings, no clear structure in the center. We see nucleus, circumnuclear regions around the nuclear source, but we don't see any clear pattern. But it has a bar, and it's very prominent bar. Okay, but the bulge is classic. In that case, we hypothesize that the galaxy might have gone to, actually has some evidence that the galaxy might have gone through a minor mergers near the nucleus, and that's why it has a classical bulge. But this is a special case. I think most of the galaxies, if I'm not mistaken, they are all pseudo bulges.
Also because in our results, so we found this structure, but very confined in the inner part of the galaxy. I mean, it has to survive just in the inner limbar resonance and the inner outer limbar resonance in the very confined region, in this place where you have these perpendicular orbits to the bar that we call X2 orbits. So just in that region, we can find this structure. And if in the cases when we didn't assume this component, we are not able to construct an inner ring. So it was a really interesting. So that's why I wanted to ask you. Thank you very much.
Thank you.
More questions?
All your galaxies have an inner limbar resonance.
Yes.
And do you know the reason for the difference, why some of them produce a ring and the others have a more flocculent distribution within the ring?
Well, that's what I said. It is going to different phases of existence. So the ring was there.
Those are transients.
Well, I don't know. I think that the ring was there, it was dissolved, and we are seeing now the galaxy without the ring. Okay, so that's. But the inner black is there. Like it could happen at any time, because we have the main perturbation and we have gas orbiting there. You know, the whole center, the whole parts of the galaxy. We have that.
Okay, thank you.
More questions? Thank you again.
Thank you so much. Wow, it's over.